All right, welcome to The Explainer. Today, we are diving headfirst into one of the most, mind-bending ideas in all of science. Seriously, it's a concept that really makes you question everything you think you know about space, time, and, reality itself. And it all starts with this legendary phrase from Albert Einstein himself. He called it spooky action at a distance. Now, the funny thing is, he meant it as a jab, a way to say this whole idea was just too weird to be true. But he accidentally gave this bizarre quantum connection the perfect name. So what was this big puzzle? What got under the skin of the world's most famous genius? Well, it all kicks off with this simple but totally bizarre idea. You can have two particles that are created together. And from that moment on, their fates are, they're linked. Instantly. And it doesn't matter if they're right next to each other or on opposite sides of the universe. Okay, so physicists have a fancy term for this. They call it a non-separable state. But what does that really mean? It means you literally can't describe one of these particles without also describing the other one. It's like they stop being two separate things and just become one single unified quantum system. And this is where it gets really trippy. The key here is this perfect anti-correlation. So picture this. We have our two entangled particles. We send one to Alice and the other one to Bob, who's maybe light years away. Now, in a typical setup, neither particle has a definite spin until you look at it. But the very instant Alice measures her particle and sees it spin up, she knows with 100% certainty that Bob's particle is spin down. It's that instantaneous connection that just felt, you get it, spooky. Yeah, you can see why this whole thing just didn't sit right with Einstein. I mean, to him, it seemed to break the most fundamental rule of the universe, that nothing, and I mean nothing, can travel faster than the speed of light. And this kicked off one of the biggest scientific debates of the 20th century. It was a real clash of titans over the very nature of reality. Okay, so this slide really lays out the two battle lines in this great debate. On one side, you've got Einstein and his idea of local realism. This is basically common sense, right? It says things have definite properties even when we're not looking, and info can't just teleport across the universe faster than light. So Einstein figured quantum theory must be missing something. There must be some hidden variables, like a secret instruction manual the particles carry with them from the start. But then on the other side, you've got the quantum view. It says, nope, the properties aren't real until you measure them, and that connection is instantaneous. The universe is just fundamentally weird and interconnected in a way that our brains struggle with. For almost 30 years, this was pretty much just an argument for philosophers and physicists to chew on. I mean, how could you possibly test something so fundamental? It really seemed impossible. But then, a physicist named John Stuart Bell came along and had this absolutely brilliant idea that turned all that philosophy into real, testable science. So here's the thing. Bell didn't even try to find those hidden variables that Einstein was so sure about. No, he did something way, way smarter. He created a mathematical rule. It's called an inequality that any theory based on Einstein's local common sense reality would have to follow. It didn't matter what the hidden variables were. If reality was local, it had to play by Bell's rules. So he worked out this specific value, this number called S, which was based on how correlated the measurements of the two particles were. And here's the bombshell. He proved that if the world works the way Einstein thought it did, S could never, ever be greater than 2. Just 2. That number became the ultimate red line for our classical reality. Okay, but here's the real kicker. Quantum mechanics made a completely different prediction. It said that because these particles are really part of one big system, their correlations would be stronger, strong enough to push that SAS value all the way up to about 2.828. And just like that, you have a clear, measurable test. If the experiments found a number bigger than 2, it would be game over for Einstein's local realism. It would prove that our universe really is spooky. So now we have a test, a real test. Physicists could finally stop arguing and just ask the universe directly. Which reality is it? Is it Einstein's common sense world or the strange, interconnected world of quantum mechanics? The race was officially on. And this journey, it took decades. It all started with that thought experiment way back in 1935. Then Bell made it testable in '64. And then, in 1982, a French physicist named Alain Aspect ran a series of truly groundbreaking experiments. His results were the first really strong evidence that reality was breaking Bell's rule. And over the next 30 years or so, scientists just kept tightening the screws, closing every possible loophole, until finally, in 2015, they ran what are called loophole-free tests that sealed the deal. And the results? Well, after all those decades and countless experiments, the verdict is in. It's unanimous, and it's undeniable. The correlations we actually measure in the real world, they consistently blow past that classical limit of 2. Reality violates Bell's inequality. Einstein's spooky action at a distance? It's real. Okay, so hold on. If this action is instantaneous, does that mean we can build a superluminal telephone and send messages faster than light? Well, as cool as that would be, the answer is a surprising no. And there's a reason for it, called the no communication theorem. See, even though the correlation is instant, the result Alice gets is totally random. It's a 50-50 shot, up or down. She can't force her particle to be up just to send a 1 to Bob. So, the universe is spooky for sure, but it's also clever. It protects causality and keeps that cosmic speed limit intact. So, okay, we've gone from a puzzle to a proven fact. This spookiness is a fundamental feature of our universe. The next logical question is, what can we actually do with it? And this is where a deep philosophical question starts turning into some truly world-changing technology. One of the most mind-blowing applications is basically unhackable communication. There's a method called quantum key distribution. Alice and Bob use these entangled particles to create a secret encryption key. But here's the genius part, step 3. They use a bunch of their measurements to run a quick Bell test. If that S value comes out greater than 2, they know their quantum link is secure. But if some eavesdropper tries to listen in, they'll break that delicate entanglement, the S value will drop, and bam, Alice and Bob know instantly they've been compromised. It is literally security that's guaranteed by the fundamental laws of physics. And it doesn't stop there. Entanglement is also the absolute secret sauce that gives quantum computers their unbelievable power. It's what lets a handful of quantum bits, or qubits, process an exponential number of possibilities all at the same time. This quantum parallelism is the engine that drives algorithms that could one day crack every code we have, or design new drugs and materials, things that are completely impossible for even the most powerful supercomputers we have today. So think about this journey we've been on. We went from Einstein's gut feeling that something was wrong to a proven physical fact about our universe that we're now starting to use. Entanglement really forces us to accept that reality is just so much stranger and so much more deeply interconnected than we ever could have imagined. It's not just a curiosity anymore. It's a resource that's building the next wave of technology. Which really leaves us with one heck of a final question, doesn't it?